Hi, this is the part 2 of fifth lecture of the advanced course of Geostatistics, focused on spatial uncertainty assessment. In this part 2, you'll see methods for the stochastic simulation of categorical variables. We saw categorical variables that can represent lithologies, ore types, rock types, soil and sediments, contaminated soil and sediments, etc. And we'll use the indicator formalism for characterizing the categorical variables through sequential indicator simulation. Suppose a categorical variable, categorical vector, x1, x2, xk categories. In the first step, we define a categorical variable for each category. Okay, that in this way, an indicator variable that takes the value 1 if at the location x belongs to xk, otherwise takes the value 0. Note that just one thing, we have used this indicator variable to characterize the classes of a continuous variable. Now we are using the same indicator, slightly different indicator to characterize categories. And the difference is in the subscript here, k. It means the class that I want to categorize here. So for any given category, we can define the mean which is the proportion of the category xk in the entire area. So in the second step, we calculate the estimated probabilities of a point randomly chosen in a regular grid of points covering the entire area A, this one, by using the indicator kriging that we have learned in the part 1 of this lecture. Okay, the spatial continuity of different categories can be assessed by the indicator variables. Okay. So, as this estimation of this category the estimation is made independently of each other, I do not guarantee that the sum of all probabilities is 1 at the end. So, in this stage, we can make some correction for any eventual violation of order relations, such a way that the sum of estimated values must be 1. So it's a simple correction to assure that the sum of all estimated probabilities sum up to 1. After that, a pseudo-cumulative distribution function can be calculated with estimated probabilities of the different categories. So the first class of cumulative distribution function, of pseudo-cumulative distribution function, is equal to the estimated probability of the first category. The second class of CDF is the sum of the first estimate, the estimate of the first category plus the estimate of second, and so on, until we reach the upper limit is the probability 1, the cumulative distribution function. Okay, we call just one detail, we call pseudo-cumulative because there's no order relation. So we could choose for the first class not the category 1 but the category 5 or 6 and so on. So there's no order relations, but the pseudo-cumulative distribution function which will perform identical function that we wish. So now we have the local cumulative distribution function, and we can now generate a first simulated value at the location xu. So we generate a value p uniformly distributed between 0 and 1, is a random number. And in XU belongs to category K if P it drops in this interval here, okay, or there, or any other interval, okay. So the simulated values after the simulation of first value, the simulated values are headed to the sample values to condition the next points to be simulated. This sequence from this point from 2 to until 6 is repeated until all points of the regular grid of A are simulated. So this is an example of three classes of a contaminated soil. Here are the sample representing the representation of the samples, where the samples were classified according to the mercury and plum contamination here. And this is an example, just an example of three simulated realizations. Note that we can compute for any spatial location XU. For example, we can compute the probability of XU to belong to any of those three classes, like by just doing the averaging of the indicator, the simulated indicator in each at that location. But more important than this probability is this measure of uncertainty, which is the Shannon's entropy, can be used as a measure of uncertainty. Essentially, this uncertainty measurement tends to be high at the boundaries where the probability of different categories are very similar, and low inside one category domain where there's one dominant category xi, for example, in terms of probability. Here, for example, look at this. Here in this corner, we can easily see that all images have the same red class. So the probability of any of those pixels to belong to the red is very high, low, and it tends to have a low entropy. Let me tell you that in case of a boundary of just two categories, we have just one indicator variable. And in that case, the indicator variance that we have seen before can also be used as a measure of uncertainty for those cases. So let's see one eventual correction for eventual problem, which is local probability correction. Let's see, when one category K, suppose, have low proportions, the sequential simulation has sometimes difficulties in reproducing that mean value, the target mean value. Suppose this is illustrated with this sketch here. We have similar proportion categories, the blue, red, and green, but we have just a low proportion category represented by this yellow. And at the end, normally at the end of the simulation procedure, the sequential simulation procedure, because it starts by a random pass over regular grid, it's a bit difficult to reach the areas of influence of this yellow category. So the final proportion of simulated values of this category tend to be underestimated. So, considering mk, the objective proportion of a given category K is the global proportion that we wish the simulation reaches, and in the random pass step S in the middle of this simulation procedure, the resulting proportion of simulated values of category K until S, let's suppose, is ms of K. So what we wish, the objective is to correct the deviation between the target M, between the reach proportion at that step S and the target MK. So we calculate the deviation between the target and the actual value MK here. this deviation here, and in each step of the random path we correct through this deviation. Okay, we correct the estimated probabilities of this deviation. So let's see, for example, let me show you a simple example of 6 little classes a simulation process in 100,000 nodes. As you can see, lithophase 6 is a small proportion of lithophase. At the very beginning of the process, a random process starts with a huge deviation and never corrects it. It ends up with a great substantial deviation. Normally tends to be underestimated. Okay. The reason of that, let me remind you, is this process assumes that stationarity between all categories. As this one has low proportion, there's a kind of non-stationarity, and this is a result of this non-stationarity. Now let's see, and in the right hand side, if you apply the correction that you have seen before, you see at the very beginning the lithophase is corrected by this deviation, and never, we do not need any further corrections. Okay. So let us see very briefly other methods to simulate categorical values. Because they are out of the scope of this course, we will see those methods very briefly. Okay. So the first one is truncated Gaussian simulation. So this truncated Gaussian simulation is based on a simulation of a Gaussian variable. So the first thing we have to do is to transform the categorical sample values, because we have sample values, we have to condition to the sample values. We have to transform the categorical sample values into Gaussian values. Second, we simulate a Gaussian variable. Is here represented by the density, the probability density function here. And we truncate the values of this density function, probability density function, according to the proportion of each lithophase. 10%, for example, 10%, 30%, 70%. And those values here of the simulated Gaussian field here are transformed, are classified according those two results here. And this is the result of truncated Gaussian. This method is extremely simple. This is the main advantage of the method, but it has some problems. First one is transformation of the categorical sample values, lithophases, in Gaussian values. We have to transform these zeros and ones in Gaussian. To transform a set of zeros, experimental sample values, in a continuous variable, you must rank the zeros and ones by determining which zeros are more zeros than the others. So these cannot be randomly ranked, otherwise it increases the negative effect at the end. Okay, so we have to choose auxiliary variable, whatever, to make sure that these zeros are transformed in Gaussian without increasing the negative effect at the end of the simulated values. Now the second problem is that the simulated values reproduce the Gaussian variogram, not the spatial continuity pattern of each litho class. Remember, in the previous method, that in the indicator formalism, each class is created with the variogram of the category. Each category is created with its own variogram and reproducing the main spatial patterns of those lithophases. So another method, which is an extension of the previous one, but is pluri-Gaussian simulation, and instead one Gaussian field is simulated, one Gaussian variable. We simulate two Gaussian variables with different patterns. Okay, like those ones. This is illustrated by those ones. And we impose results, not we impose results joint results on both Gaussian fields, simulated Gaussian fields, and this is the result here. So the results are defined according to spatial relationship between facies. This is obtained at dual data or other source of information, outcrops, etc. So this is the last method that I want to talk to you is a it is called multi-point geostatistical methods. Remember that all the methods that we talked until now each are based in a 2-point, which is called 2-point statistics, are based in a variogram or covariance. And this method here, the multi-point geostatistics, multi-point simulation, is based not a variogram but a reference image. The reference image is obtained through expert opinion or any outcrop or any other source. Okay, and how it works? Okay, it is a sequential simulation method, follows a sequential simulation method. For example, suppose that in a random path, we found this pattern here, which is those four sample values, U1 to U4, and we want to know the probability at this target location, XU, okay? So we have two yellows. This is the reference image that we have a yellow rock and some blue channels inside the yellow rock, okay? So, and we have two yellow values and two blue values here. What we do, we take this pattern and we'll see how many times this pattern is replicated in this training image. Of course, this is an illustrative case. So, and you can see that this pattern we can find 1, 2, 3, 4 times. This pattern you find that in those 4 times the target XU in this case is blue, 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 and yellow, which means that at the end of this searching process, we have the probability searching process through the training image. We have the probability of this XU to be blue is 3/4, and probability to be in the yellow rock is 1/4, and that's it. That's so I generate one random number, and I could generate one simulated value of a categorical variable for this location U. Okay, that it works like that. So this is the training, just to show you. This is a training image as is unconditional simulations here. Okay, possible conditional simulation. This method, we obtain after we obtain a final image, we can do some geometrical transformations, rotation, enlargements, and so on.